So it is my great pleasure, to introduce Ilir Snopçe from Federal University of Rio de Janeiro, who is going to speak about test elements and retracts in free groups. Please.
Okay, Pavel, thank you very much for the invitation. It is always a great pleasure for me to speak in this seminar. Okay, I always feel like I'm at home. Okay, I'm going to talk about test element and retracts in free groups. So let us start with a simple definition. A retract of a group G is a subgroup H of G for which there exists a homomorphism R from G to H that restricts to the identity on H. Okay, so just keep this in mind. If there is a function, a homomorphism from G to H which restricts to the identity on H. And in this case, we call this our retraction. Okay, what are examples of retracts? So there are some simple examples that everyone knows. The first one, every direct factor is a retract. Of course, when you have a direct factor of a group, we can project this direct factor to itself by the identity map and send the rest to the identity element, right? In this case, we have a homomorphism, which is a retract. Other examples of retracts are free factors. Okay, so every free factor is a retract. So since the topic of today's talk is free groups, so we are going to talk about free groups. Of course, in the case of free groups, we cannot have a proper retract, which is a direct factor, but there are plenty of free factors. But one may ask, are there any other examples of retracts in free groups? So let us try to analyze one single example here. So let us denote by f of x, y, the free group with basis x and y, okay? And let us consider this map here, this basically endomorphism. R of x is equal to x times the commutator of x and y, and R of epsilon is equal to 1. Then it is easy to see that R of x, commutator x and y, is exactly this element here. Why? Because here in the commutator, y and y inverse are going to 1, x and x inverse, they will be simplified in the image. So we just have R of x, which is exactly this element here. So from here, we obtain that the cyclic group generated by this element is a retract of the free group of rank 2 on the basis x and y. And actually, it is not difficult to see that this cyclic group is not a free factor. So this shows that in free groups, there are retracts which are not free factors. And let us just try to see, just spend a few seconds here. So what do we have here? We send x to x times commutator x and y. But this commutator of x and y belongs where? To the normal subgroup generated by y. And we send R of y equal to 1. And actually, this idea, one can use this idea to describe all the retracts in free groups, okay? So before stating a proposition that will show this, let me just say that throughout this talk, F denotes a free group of finite rank, and F of Fn denotes a free group of finite rank n. So now we have the following proposition. This proposition is an exercise in the book of Magnus Caras and Solitat. So what does it say? If H is a subgroup of Fn, then the following conditions are equivalent. H is a retract of Fn of rank k, and there is a basis x1, x2, xn for Fn, so that H is freely generated by W, consisting of W1 up to Wk, where Wi is xi ni. Okay, and what are ni's here? Ni's belong to the normal subgroup generated by the other generators. So by xk plus 1 up to xn. So again, so we have here xi, where I goes from 1 to k, ni. But all these ni's are coming from the normal subgroup generated by the other generators, by the remaining generators. And of course, in this case, a retraction R is given by R of xi is equal to xi times ni, when I runs through from 1 to k, and on the other side, R of xi is equal to 1 for the rest, for the other possibilities of I. And this is exactly what happens in the previous example that I said. So this is a fairly explicit description of retracts in free groups. But it is surprising that even though we have such an explicit description, it is extremely difficult to answer even some very simple questions. For example, if I ask you, is it true that the intersection of two retracts is again a retract? I think it's very difficult to answer this question. And towards the end of my talk, we will see a kind of result relating to this question. Okay, so now how one can study.
Wait a minute, Ilir. I just slow you down a little bit. This NI depends on I, on XI, or I mean,
you see, Pavel, we
it is
have
normal closure of
here. You see, you have this basis here,
yes,
and we choose. Of course, the first observation is that the rank of a retract is at most n. It cannot be more than the rank of the group. So no, there are n generators. So if you look at here, we choose, of course, we can order these generators as we want. So in order to obtain a retract, we choose x1, x2 up to xk generators, right? And we take these wi's, which are these xi's times ni. But those ni's now belong to the normal subgroup generated by the remaining generators.
Which means xk plus 1 xn?
Exactly. So if you look at
but
here,
then ni depends on k, not about on I, really.
Which one here? Yes, but I think
ni is always generated by k plus 1 xan. So it is just one normal subgroup.
Yeah, but N1, N2, and Nk belong to the normal closure or to the normal subgroup generated by xk plus 1 up to xn. So it's difficult to write it down.
Right. So they are not equal. They just normal subgroups of the normal closure.
Exactly.
Okay. Right.
Ilir, one more question. You have W is this element equal to the class. What do you mean by this?
This W? Those are just
W
elements.
is element on the right, but on the right is a class.
It's not a class.
But
this Ni is not a subgroup. Ni is just any element which belongs to the normal subgroup.
Ni in the normal subgroup.
So you see, let us go back. So our Ni, here we have x1 and x2. x1 is our x. Our N1 is the commutator xy, which belongs to the normal subgroup generated by y. Right? And that's it. Okay. So now let me define another notion. The notion of a test element, which I have defined in this department a few times. So a test element of a group G is an element G in G with the following property. If phi of G is equal to G for an endomorphism phi from G to G, then phi must be an automorphism. So what is a test element? Whenever an endomorphism fixes this element, it must be an automorphism. Okay? So actually the idea here is to distinguish automorphism among all endomorphism by the means of their action on a single element, which is called the test element. And this notion was introduced by Spielrein in 1995. But actually the first example of a test element was given to us by Nielsen more than 100 years ago. So let f of x1, xn, you know the free group is basis x1, x2 up to xn in the rest of this talk. Nielsen proved that the commutator x1, x2 is a test element of f of x1, x2. Okay? And this result was generalized after 50 years, more or less, by Tsi Shank, who showed that in a free group with basis x1, x2, x2m, this product of commutators is a test element. Okay? And another result in this direction was proved by Rips. Rips actually proved that higher commutator of weight n with arbitrary disposition of the commutator bracket is a test element of a free group with basis x1 up to xn. But of course, it is not true that all test elements are commutator elements. There are other test elements as well. So one such an example is given by Turner. So if you look at a free group with basis x1 to xn, x1 to the k1, x2 to the k2 times up to xn to the kn is a test element of the free group if and only if all the exponents here are non-zero and the GCD of the exponents is different than 1. So more or less it characterizes these elements of this form here, okay? So now let us think for a second. Let us try to connect the notion of a retract and test elements, two main concepts of this talk. So let us suppose that we have an element which belongs to a proper retract. What can we say? Can this element be a test element? Of course, it cannot be a test element because the retraction map fixes this element, but its image is not the whole group G, it's a proper subgroup. And actually, Turner proved that the converse is also true. And this is a very nice characterization of test elements. So basically, we have the test elements of a free group F of finite rank are exactly the elements not contained in any proper retract of F. Okay, so the other way around is also true. And actually, after getting this result, people started to ask, okay, are there any other groups which satisfy this property? Therefore, it was introduced the notion of a Turner group. So group G, whose test elements are exactly the elements not contained in any proper retract of the group, is called the Turner group. So whenever one can characterize test elements, as in this theorem of Turner, if this is possible in a group, we call this group a Turner group. And of course, free groups are examples of Turner groups, but other examples of Turner groups are finitely generated Fuchsian groups. And this was proved by O'Neill and Turner. And more recently, it was proved by groups that all torsion-free hyperbolic groups are Turner groups. Okay? So now the question is, since we have all these technical notions here, concepts, one may ask, okay, we know that in free groups there are test elements, but how many test elements are there? Or how are they distributed? And it's the same question for the retracts. In order to explain this kind and to try to answer these kind of questions, we need some extra concepts. So let me try to make some other definitions. So let G be a finitely generated group with a finite generating set X. Okay. Let us denote by BXR the ball of radius R centered at the identity in the metric space G dx, where dx is the word metric on G with respect to X. So we are considering the word metric, and in this metric space, we define the balls. Now, given a subset S of G, the asymptotic density of S in G with respect to X is defined as follows. We take S intersection balls of radius K, we take the cardinality of this set, we divide this cardinality with the cardinality of a ball of radius K, and we take the limb sup when K tends to infinity. And in this way, we define the asymptotic density of any given subset of G. When this asymptotic density is 0, we say that the set is negligible. If it is 1, the set is generic. And now, actually, for example, if you look at the set of all proper powers in a free group, it was proved by Olshansky and Arjantseva that this set is negligible. So it has asymptotic density 0. Or if you look at primitive elements, at the set of all primitive elements, this is also has an asymptotic density 0. And of course, the complements of these sets have asymptotic density 1. But it is interesting to note that for all among the subsets of a free group for which the asymptotic density has been studied and which could be defined by some interesting algebraic property, we get, most of the time, either we get negligible sets or generic. So it's very rarely it could happen that there is an example where we get an intermediate asymptotic density. But one such result was obtained by Kapovic, Rybin, Shoup, and Spielrein in 2007. Actually, they proved the following. Let T be the set of test elements of a free group of rank 2. Then T has intermediate density, different from 0 and 1. Okay? So in the case of free groups of rank 2, the density, asymptotic density is intermediate. More precisely, they have these bounds here. They gave the following bounds, okay? But in the same paper, they asked the following question. Let there be a free group of rank n greater or equal to 3. Is the set of test elements of F negligible or of density 0? And okay, I may wonder here why the question should be stated in such a way when in the case of rank 2, they already have an intermediate density. But the reason is that if you think of the theorem of Turner, an element is a test element if and only it does not belong to a proper retract. But in a free group of rank 2, the proper retracts have rank 1, so they are cyclic. And it's very easy to control the situation. It turns out that there are many test elements in a free group of rank 2. But when one goes to higher rank, this doesn't happen anymore. And some computer calculations actually gave an evidence that there should be very few test elements. So that's why they made this question. Now, before trying to answer this question, I have to define one more concept, which is a concept of a net. So again, let G be a finitely generated group with a finite generating set X. Okay, I will say now, I just forgot to say that basically this talk is based on a joint work with Slobodan, Tanushevski, and Pavel Zalesskii. Pavel will be involved in a few minutes, slightly later. Okay.
It was written, in fact.
Yeah. Okay, just in case, because I always want to emphasize that. So let G be a finitely generated group with a finite generating set X. A subset S of G is called the C net with respect to X if every element of G is in distance at most C from S. Okay? So what does this mean? S is a C net if we can cover the entire group with balls of radius C centered at the elements of S. So this is the notion of a net. So our result, which answers basically the question of Kapovich, Rybin, Shupich, Pilrain, is the following. The set of test elements of a free group Fn of rank n greater or equal to 2 is a 3n minus 2 net with respect to every finite generating set of Fn. Okay? And from here, we obtain that the asymptotic density must be positive. So in particular, this set, the set of test elements of Fn, has intermediate asymptotic density in Fn. So the same phenomena happens in all free groups of finite rank. There are plenty of test elements. And the fact being a net gives you a stronger evidence that the test elements are really nicely distributed over the free group. Okay? Good, but now, so we have this theorem, and let us recall again, let us try to use the theorem of Turner. The characterization of test element using the language of retracts that Turner gave yields the following corollary of this theorem. The union of all proper retracts of a free group of rank n greater or equal to 2 has intermediate asymptotic density in Fn. Okay? And it is interesting to compare this result with the case of free factors. It is known that the union of all proper free factors of a free group f of n of rank n greater or equal to 2 has asymptotic density 0. Okay? So there are much more retracts than free factors. And before trying to give an idea how one can prove such a result, I would like to mention that we have a similar result. The same holds in the case of orientable surface groups of genus greater or equal to 2 and non-orientable surface groups of genus greater or equal to 3. But here I will just concentrate on 3 groups. So what is the idea here? The idea is to use the concepts which is well known in your department, actually, in Brasilia, the concept of profinite and pro-p groups. So we are using pro-p techniques in order to prove this theorem. So let us recall briefly. A compact totally disconnected topological group is called a profinite group. Okay? And given a prime p, a profinite group in which every open subgroup has index a power of P is called a propy group. And equivalently, a propy group is the inverse limit of an inverse system of finite P groups. And the same holds for profinite groups. A profinite group is the inverse limit of an inverse system of finite groups. So what are examples of propy groups? Every finite P group is an example of a propy group with a discrete topology. But there is another example that everyone is familiar with, is the additive group of the ring of p-adic integers. So ZP, the additive group of the ring of p-adic integers, is an example of an infinite propy group. And actually, if you look here at this example, what is ZP? ZP is the inverse limit of all finite quotients of Z of order some power of P, right? And actually, we can use this idea to associate a propy group to an arbitrary discrete group G using the concept of a propy completion. So given a group G, we denote by GP hat the propy completion of G. In other words, what is GP hat? Is the inverse limit of G mod n when n runs over all normal subgroups of G of index some finite power of P. Okay. And actually, there is a natural homomorphism, JP, from G to its propy completion, which sends G to a tuple, Gn. So the inverse limit, of course, is a subgroup of the direct product of G mod n's. And therefore, we basically, by JP, we just send G to this tuple here. And well, an interesting thing happens when G is residually finite P. So if G is residually finite P, which means that the intersection of all normal subgroups of finite index of index P is trivial, then JP in this case is an embedding. And why this is important for us? Whenever we have an embedding, then we can identify the image of G with G inside GP hat. So G lives inside GP hat. The same thing happens here. Z lives inside ZP. Okay, so now let me give you the two main ingredients in the proof of theorem A. So the main ingredients in the proof of theorem A are the following. The first theorem, which we proved with Tanushevski in 2017, is the following. The test elements of a finitely generated profinite group G are exactly the elements not contained in any proper retract of G. In other words, every finitely generated profinite group is a Turner group. Just to close the window. Okay, so basically we proved that all finitely generated profinite groups are Turner groups. So this is one of the key ingredients. And another thing that we are going to use is the following fact. So actually, if you think on test elements, and in general, we don't know what is the relation entry between G and the propy completion of G. But when G is residually finite P and Turner, then there is a very nice connection, which is given by this theorem here. So let P be a prime, and let G be a finitely generated residually finite P Turner group. If G in G is a test element of the propy completion, of course, G belongs in GP now, because we just said, in this case, the embedding, we have an embedding. So G, we can assume that lies inside the propy completion. So if G in G is a test element of the propy completion, then G is a test element of G. Okay? So we have this result. Whenever G is a test element of the propy completion, then G is a test element of G. And of course, this theorem allows one to use the theory of propy groups or propy techniques in order to attack problems about test elements in discrete groups. Of course, whenever these groups are residually finite P and Turner. So now let us go back to our example, right? So what do we have in our case? We want to show the asymptotic density set that the set of test elements in a free group of finite rank forms a net. Of course, free groups are what? Free groups are residually finite P, and we know that they are Turner. So that's why, in the case of free propy groups, we can apply this second theorem here. But moreover, I have to say one more fact. When we are inside free propy, so the propy completion of a free group is a free propy group, which is a free object in the category of propy groups. And if you have a basis X of F, then X is also a basis of the propy completion. So now one simple observation leads to a very tame theory of test elements in propy groups, in free propy groups. And what is this observation? When you are inside of free propy groups, the only retracts are free factors. Okay? So in discrete, this is not true, but in free propy groups, the only retracts are free factors. So therefore, and it's much easier to work with free factors. So therefore, we developed a nice theory of test elements with Slobodan in the case of free propy groups. And now what is the idea in our case? Let us take an element, any given element in a free group of finite rank. Then we go to its propy completion. When we go to its propy completion, then we can find a word of finite length, right? When we multiply this word with the first given word, we will obtain a test element in the propy completion. But by this second theorem here, we will obtain that this element is a test element inside the free group. So more or less, this is the idea how one can attack this type of problems. Okay, but I would not like to say more in this direction. Then I will try to move slightly in a different direction. Okay, so now we will start the second part of the talk, which will use some ideas from the first part. Okay, so now let S be a set of endomorphism of a free group of finite rank F. The fixed subgroup of S is defined by all elements in F, okay, which fix W. So this is the fixed subgroup of S, where S is a set of endomorphism of a free group. So actually the study of fixed subgroups was initiated basically, I think, in 1975 by Scott and Dyer. They proved some interesting results at that time. But basically this line of research, in particular, the bound the rank of these fixed subgroups of S, was a very active area in the 80s and 90s. So where people obtained many interesting results in this direction. But the deepest result, everyone agrees, is the following result, which appears in the seminal paper of Bestvina and Handel, where they introduce the concept of a train track and use that concept in order to prove this theorem. So the result is the following. For every automorphism alpha of F, the rank of fixed alpha is less or equal to the rank of F. Okay, so you can bound the rank of the fixed alpha with rank of F. Of course, this fixed alpha is a subgroup here, so it's a free group. It is inside F. Then the question is, can we bound this rank? And actually, can we bound actually this rank in general? This is what was known at the time as a Scott conjecture, okay? So this was the first important step in the direction, a deep step. And actually, Imrich and Turner used a clever algebraic argument to derive immediately from the result of Bestvina and Handel the following, that for every endomorphism phi of F, the rank of fixed phi is less or equal to then the rank of F. Okay, and actually before I go on, yes?
There's a difference here. This is 92, this is 89. Which is before which?
Ah, this is 92. Yes, a very nice observation. And I'm very happy that you were the only one who noticed that. Actually, this is the point. In this line of research, things were so active, you know, and people were working so much that quite often it happened that someone will solve a problem, will get a result, but people will apply this result and will publish paper before that. So Handel and Bestvina, they proved the result in 1988. And it took about 4 years to publish this paper. And this was notoriously hard to read. It was published in Annals of Mathematics, but it's a very difficult paper of topological flavor. So that's why the result of Imrich and Turner appeared in 89. But it's a very nice observation.
I think actually area started with the result of Gersten, which was published in 87, that automorphism of fixed points, well, that fixed points of any automorphism of free group is finitely generated. I think this was the first result in the area. And then it was sort of blow up.
So the first result in the area is since 1975, where Dyer and Scott proved that if you have an automorphism of finite order, or if this
exactly. But
is finite, then fixed S is a free factor. So
absolutely.
Moreover,
yes. But this was particular case, automorphism of finite order. And Gersten proved it for any automorphism. Yes.
And you are completely right. And it was in 1983 when Gersten proved that all of them
83, not 87,
And I would like to mention, that's why I started to mention, and then we moved to a different direction. Actually, I have to say that in the case of propy groups, many questions are still open, and Pavel is one of the main contributors in this direction. So he has done a fantastic work in this direction, but unfortunately there is much more to be done. So but I will not talk about it today, okay? But in particular,
but this kind of theorems that you are putting here for propy case are open actually.
Yes, of course. I think that I can just say that in the propy case, the automorphism group of a pre-propy group is virtually propy. So there might be automorphism of order which are co-prime to P. And in this case, Px alpha is of infinite rank. So I think Pavel has proved this result with Rebus and Herford.
No, it is just Rebus and Herford. It was just, it was without me. It was.
But anyway, I think that there are interesting things there. But when the order of alpha is a power of P, or alpha is of infinite order of power of P, this is widely open. No one knows anything. Okay, so now let us move in the discrete case where we are now. So we have this S here, okay? We have S, and we can, for single automorphism, endomorphism, we know that everything holds. But in what happens in general, when we have an arbitrary set of automorphism, endomorphism? In order to discuss what's going on in this direction, let me just try to make a definition. So subgroup H of F is said to be inert if the rank of H intersection K is less or equal than the rank of K for every subgroup K of F. Okay, so this is inert. And in particular, note here, if H is inert, if you take K to be F, then we have that the rank of H is less or equal to than the rank of F. So that's why this notion is connected basically to these two results. And the next interesting result in this direction is the result of Dix and Ventura in 1996, which proved that if S is a set of injective endomorphism of F, then fixed S is inert in F. In particular, the rank of fix of S is less or equal than the rank of F. So actually the Scott conjecture was also proved whenever we have an arbitrary set of injective endomorphisms. Okay, and actually Dix and Ventura, they interpreted the theory of Handel and Bestvina using algebraic language and extended it slightly, and they got this beautiful result. In the same paper, they asked the following, and they made the following conjecture, which is known as inertia conjecture. If S is a set of endomorphisms of F, then fixed S is inert in F. Of course, if fixed S is inert in F, then we will have this bound here, the rank. And it turns out that this is equivalent, so this conjecture is equivalent to the following. Equivalently, every retract of Fn is inert. So using observation of Turner, or a kind of lemma from Turner, one can show that these two assertions are equivalent. So in order to finish completely the Scott conjecture, one just needs to prove that every retract of Fn is inert. Actually, a person who really spent time working in this problem was Bergman, and he finally managed to prove completely the Scott conjecture. So Bergman proved that for any set S of endomorphism of F, the rank of fix of S is less or equal to the rank of F. So he proved this in the paper was published in 1999. So here, the story with the Scott conjecture ends. But of course, actually in this paper, Bergman was not able to prove that the inertia conjecture. Okay, so still it was not clear in this paper if X of S is inert. Nevertheless, in the same paper, Bergman obtained another interesting result, but which surprisingly has a very difficult proof. So the intersection of any family of retracts of F is a retract of F. So this was not known until 1999, and then Bergman proved that this result holds. In the beginning, I told you, okay, can we answer the question, the intersection of two retracts is retract? And this question was answered by Bergman. But if you compare to the case of free factors, the intersection of free factors is a free factor. I think that is an exercise for graduate students when they do the course of combinatorial group theory. But here it's quite a deep result. In the same paper, Bergman raised the following question. Let H be a free group of finite rank, and let R be a retract of F. Is H intersection R a retract of H for every finitely generated subgroup H of F? So again, what is the question? So we take a retract of F, and if you intersect this retract with any other subgroup, is this intersection a retract of this subgroup? In the case of free factor, this is true, and it's not a difficult result. But here it was not known. And actually, this question is a very interesting question on its own right. And if the answer is positive, then it might have some important implication, immediate implications. But on the other side, one special reason why Bergman was interested in this question was the following observation. Affirmative answer to Bergman's question implies inertia conjecture. Okay, this is an additional motivation to think about this question. And now, if you recall, in October, André Heiking gave a beautiful talk about inertia conjecture. So actually, the inertia conjecture was proved recently by Antolin and Heiking's appearance. Okay. Now, of course, and now, but regardless of this, now I will try to discuss the Bergman question. Okay, so when we were working, we spent the time on working on Bergman's question much earlier than Antolin and Heiking's appearance. And of course, we wanted to obtain inertia conjecture and to prove a positive result in this direction, but we were really interested on the question on itself because this was an important question. And the next theorem gives a complete answer to the question of Bergman. So this is a theorem, a joint work with Slobodan, Tanushevski, and with Pavel. So what do we have? Let H be a subgroup of a free group of rank n, of 2. Let H be a subgroup of, so we have a free group of rank n, okay? And let H be a subgroup of this free group of rank 2. So H has rank 2. And let R be a retract of Fn. Then H intersection R is a retract of H. Okay? So when we intersect subgroups of rank 2 with retracts, we again obtain a retract of this subgroup. But on the other side, unfortunately, the second part of the theorem gives a negative answer in general to Bergman's question. And so what is the thing, the result? For every m greater or equal to 3 and every k between 1 and n minus 1, there exists a subgroup H of Fn of rank m and a retract R of Fn of rank k such that H intersection R is not a retract of H. So this covers all the possibilities because a retract can not have rank larger than n, and if it has rank n, it is Fn. So we cover all the cases here. Therefore, this theorem gives a complete answer to the question of Bergman, okay? Of course, actually, the first part is a positive result. And for a long time, we were optimistic that the theorem will hold in general, okay? There were some kind of obstructions which led to some other interesting results, but eventually we realized that there is a counterexample and the result is not true. Okay. So now during the rest of my talk, I will try to give some ideas what is going on here in this theorem. The first observation is that this part 1, it uses propy groups. In particular, many recent results about test elements in free propy groups. Okay, and the second part is of course, it's of, since we construct things, it's of geometric flavor. But in order to find this counterexample, we were led when we were thinking about proving Bergman's theorem. So now, as I said, the first part depends on the theory of propy groups. And the key ingredient is the following result, which is actually my favorite result in all this subject. And you will see in a moment why. So in the proof of the first part of the above theorem, the key ingredient is the retract avoidance theorem. Retract avoidance theorem, which says the following. Let H be a subgroup of F, and let Ri be a family of retracts of F. If H is a subgroup of the, if H is contained in the union of this family of retracts, then H must be contained in at least one of these retracts, right? And why, as we say here, retract avoidance theorem, of course, this result resembles the prime avoidance lemma. So if you have a commutative ring, and if an ideal of this commutative ring is contained in the union of finitely many primes, then it must be contained in one of them. But this is here, we don't say finitely many retracts, and it's we are in a non-commutative case. So that's why this was quite a surprising result. So now, why do I say this is a key ingredient? So let us think here. In first, we want to show that this is a retract of H. Of course, we can assume that this is non-empty. If it is identity, then it is a retract. So there are two cases. Either H intersection R does not contain a test element of H, or it contains a test element of H. So if H intersection R does not contain an element of H, then using the Turner's theorem, it is contained in the union of all proper retracts of H. So in particular, by this prime retract avoidance theorem, it is contained in one single retract. And from there, we derive that it must be equal to this retract. Okay? So the second case is when H intersection R contains a test element. And in this case, we really used almost every single result of test elements that we have obtained in a previous work with Tanushevski. But in order to generalize for higher rank of H, there is one abstraction which doesn't allow that. I will not talk about it now, but at the end, someone can ask, I will try to explain. So that's why I will finish with the first part, and I will try to give the contra-example for the second part here, okay? And try to explain the main ideas. Of course, I will not, I will just work with cyclic retracts when this k is equal to 1. But if you deal with the cyclic retract, this result one can obtain using standard combinatorial techniques, playing with free products and similar things. Okay, so now hopefully this is the last notion which I will introduce today. I made a couple of definitions, but this is an interesting definition on itself. So an element A, so an n tuple A1 up to AN in Zn is called visible if it belongs to a basis of Zn, or equivalently, if the GCD of these coordinates here, A1 up to AN, is equal to 1. So this is what is called a visible element, okay? And we can generalize this definition to free groups. So let pi AB be the quotient homomorphism from F onto its abelianization. An element W in F is said to be visible if its image under this quotient homomorphism is visible in the abelianization. Okay, so let us make clear. I think that there is no, so we just need to remember that the GCD of these coordinates is equal to 1. Then the element is visible. Why do we need this concept? We need this concept because of the following observation. A cyclic group generated by W is a retract of N, Fn, if and only if W is a visible element of Fn. Okay, so please keep this in mind until the end of this talk. So an element, a cyclic group generated by one element is a retract of Fn, if and only if W is a visible element of Fn. But now, the question of Bergman, we can translate in our attempt to find a negative answer to the following question. We have the following reformulation. let W be a visible element of F, and let H be a finitely generated subgroup of F that contains some non-trivial power of W. Okay? Let M be the smallest positive integer such that Wm belongs to H. Is Wm a visible element of H? Right? So if we can find that visible, so if the answer here is not, then the intersection is not a retract, and we are done. So what is the main idea? We want to find the element W, a visible element of F, and the subgroup H, such that the first power of W which enters inside H is not visible element of H. And how I can do this? So the first thing is that in order to answer Bergman's question, it is enough to consider finite index subgroups, because one can show using Hall theorem, Marshall-Hall's theorem, and Kura subgroup theorem that if there is a counterexample of infinite index, there will be a counterexample of finite index as well. So this is the first observation. And the second observation now is that, which took some time to realize, that if H is subnormal, then this always be a visible element. So we have to construct a subgroup which is not subnormal, in particular not normal. Okay, so let me now show you, I will continue and try to tell you how one can construct such examples. So now let gamma denote the CW complex with one zero cell and two oriented one cells, E and F. Actually, here we have a bouquet of two circles, or a wet sum of two circles with a joint zero cell as a vertex. Okay. We think of F2, so we think of a free group of rank 2 as a fundamental group of gamma, and we let X and Y stand for the homotopy classes of the loops determined by E and F respectively. So now, for M greater or equal to 2, let gamma M be a CW complex with M0 cells, B0 up to Vm minus 1, 2M oriented one cells, EI, Fi, and the origin of both EI and Fi is the vertex Vi. The terminus of EI is Vm minus I, and the terminus of Fi is Vi plus 1, where the indices are taken modulo I. Don't worry for this part. I just want to be exact, precise, so that's why I'm giving that. I will show you a picture in a minute. So actually, we have this. We have this picture for G9, for gamma 9. So we have gamma 9. So we have, in our case, we have E and F, a bouquet of two circles. But now we have this space. And it turns out that this is a covering space. And what do we have? We have F0, F1, F2, F3, up to F8 here. And then we have E1 in this direction, E8 in this direction, E2 in this direction, E7 in this direction. And actually, what can we see? Let HM be the graph map defined by HMEI is equal to E, and HMFI is equal to F for every I between 0 and n minus 1. It is straightforward to verify that this is a covering map. And actually, this one is a covering space. And now consider the subgroup HM associated. So this is the image of this, the fundamental group of gamma M B0 of F2. It was easy here to see that this F0, F1 up to F7, they form a spanning tree of this graph. Okay, and now from there, it is easy to see that the basis of HM is determined by this tree. Determined by this tree is X, T1 given with this element, T2 given with this element, Tm minus 1 and Ym. Okay, so basically we know explicit generators of HM now. But now, for k greater or equal to 1, set Wk is this element here, X, Xy to the k belongs to F2. Each Wk is a visible element in F2. Why? We already discussed this. If you recall the exercise from the Magnus book, right? We know that this element here, okay, is a retract, the subgroup generated by this element. So that's why this is a visible element in F2. And now what do we have? Now we have the following lemma. Let m greater equal to 2k plus 1 with k greater or equal to 1. Then wk does not belong to hm. But wk square is equal to this product here. But if you look here, Tm minus 1, this cancels in the abelianization with Tm minus 1. So the power of Tm minus 1 is 0 in the abelianization. And the same is holds for all Ti's. And here we have x squared. So if you look at the abelianization in the GCD of these elements, it is 2. So wk squared is not a visible element. And this answers the problem of the question of Bergman. Okay, so here I just gave like a general recapitulation what is going on to give you how we reach on these things. But now the last few minutes of my talk, I would like to dedicate to the graduate students, because I know that there are many graduate students that are watching this talk. So I will spend 3 more minutes. So let us assume that we want to solve the Bergman's problem. It was a very important open problem. And in the rest, I want to show that in order to solve an important problem, one doesn't need to know much. One has to try. Okay, so if one tries, then eventually you can solve the problem. So let me try to explain this problem to graduate students, how you should attack this problem. So I will explain as I explain calculus to my own students. Just a second. So now let us consider the homomorphism psi from free group in X and Y to D3. D3 is the dihedral group of order 6. And let us define this homomorphism. Phi of X is equal to T, and psi of X is equal to T, psi of Y is equal to S. Okay, so we have, it's easy to check, this is a homomorphism. Let K be the inverse image of psi under psi, so psi inverse of T. So T is a cyclic subgroup of D3 of order 2. Okay, so why do I do this? Well, note that T is not a normal subgroup of D3. And everyone knows that if you try to find a simpler example, a finite group of smaller order, all the subgroups there are normal. So this is the simplest example which is available to us. And we take a subgroup which is not normal. And if you take its pre-image, we obtain a subgroup K in f of xy, which is not normal. But now every graduate student who has done a little bit of Nielsen-Schreier theory can see that this K is generated, and you can guess and you can prove that it is generated by these 4 elements: X, T1, T2, Y cubed. Okay, it's a simple exercise. Now, we know from the exercise of Magnus, actually, book, that this element here is a visible element of f of xy. So R generated by W1 is a retract of f of xy, because this is a visible element. And now one can see that W1 squared is x squared times the commutator inverse T1. And of course, not a visible element, because in the abelianization, the GCD of the corresponding elements is 2. Here they just cancel. And therefore, this is not a retract of K. So actually, in order to solve Bergman's problem, it's enough to have this slide here. So that's why I would like this to be a message to students that you have to try to solve problems. Be optimistic and never give up. Eventually, you will reach your goal. Okay, thank you very much. I would like to finish here.
Well, thank you very much. Yeah, let's thank the speaker. And I open question session, right? Any questions to the speaker? Yes, please say it.
Many years ago, Snopçe was involved, and Tanushevski was involved in studying test elements for finite functions groups. I don't know much anymore about what went on after that. Do you know?
Yes, actually, that's a nice point. It's a nice question. So, okay, first of all, in this talk, I didn't leave to students explicit open problems, that there are thousands and millions of implicit open problems. So you can pick your favorite group. You can ask if it is Turner, if it contains a test element, and so on. But of course, there have been done in free groups is the main theory, and it has really nice implication and so on. But there have been done, the study of test elements has been done also in some other categories of group. And as Professor Said just mentioned, actually there is like Gupta, Timoshenko, Romankov. So they have been involved in the case of nilpotent, free nilpotent groups. So if you have a free nilpotent groups, it is very interesting fact what is going on. So it's the following. If you have a free nilpotent group of class 2 and of rank, which is an odd number, then it does not contain test elements. But on the other side, if you have a nilpotent group of higher class, free nilpotent group of a higher class in any rank, it contains test elements. And also, if you have actually of class 2, but of even rank, again, it contains test elements. So basically, what they have done, because you see at some point, people didn't know even a single example of a test element, right? In many classes of groups, so they attacked this problem, and it turned out that this is true, right? And actually, since I mentioned free nilpotent groups, it's the same thing in the case of, not the same, there have been done studies in the case of free solvable groups. And in the case of free solvable groups, if the rank of the free solvable group is 2, right, then there is a test element. But if the rank is higher, there is no test element. So they do not contain test elements, but there is a notion of so-called rank. So a rank, a test rank of a group is the minimum number of elements such that if an endomorphism fixes this element, it must be an automorphism, okay? So I think that again, like Timoshenko, Romankov, they have proved that, I'm not one of them, but they are quite related, have joint papers, that when you have a free solvable group of rank K, then the test rank is K minus 1. So this is what is known, moreover, in that direction. Okay, good.
Can I have a question?
Yeah, sure.
Yes.
Martin.
Can you go to your last slide?
My last slide. Okay.
Not this one. Okay. Because I don't understand. Because I mean I'm not used to these computations. But what did you prove here? That there exists a subgroup that is not a retract?
Yeah. Okay. Let us see. Let us see. So what do we want? We know that in order to prove that I just mentioned an equivalent version. So when we have cyclic retracts, being a retract is the same element is the same thing with being a visible element. Okay. Mm-hmm. So in order to answer negatively Bergman's question, we need to find a retract of a group, of the free group of rank 2, and a subgroup such that the intersection of the retract and the subgroup is not a retract of the subgroup.
Oh, okay.
Right? So basically, then we take this subgroup K. Then this W1 is a visible element of this f of xy. Mm-hmm. Okay? So it is a retract. The cyclic group generated by this W1 is a retract. But the intersection of this W1, okay, or this R with K is W1 square. Okay? But W1 square is not visible in K. So therefore it's not a retract of K. And that's it. Okay.
And can I ask you another thing? You said in the third bullet item, you said that this is an easy exercise using some theory. Can you repeat that?
No, the point is that, okay,
The
so
K,
this is a finite.
no, it's just Schreier formula.
you see, this is K. So we have T. T is of index 3 here, right? In D3.
Yeah.
So if you take W, the inverse image of this, you will have a subgroup of index 3 in f of xy. So this is like the minimalistic example of smallest possible index, because if it was of index 3, it is normal. Then you have how many, by Schreyer's formula, it has 4 generators.
Oh, Schreyer's formula, okay.
Yes.
Yes, so X belongs to K,
Okay.
right? But Y does not belong to K. And then just apply Schreyer's formula, and then, okay, you can try to guess to put these generators, or you can just use this Schreier-Nielsen method to get those things. Of course, what I am giving you now is like, once the picture is clear, the example is clear, but it's not always. Sometimes it may take 15 years to get the right example, or even more, you know, so this is the point. But once we really, this is the point why it doesn't work.
Mm-hmm.
So, and it's good that we didn't realize this earlier, otherwise we wouldn't prove some other interesting results which were inspired from these questions. And why we didn't realize this earlier is the fact that we never in the beginning thought that the cyclic retracts will give a contra-example. It's really like, because many good mathematicians have tried to solve this problem, many significant people, and yeah. But then actually this contra-example, in some sense, with Pavel, we were working in Düsseldorf, let's say, the whole day trying to prove some, I don't know what kind of theorems, and then we decided to take a break. And the first idea was exactly during this 20 minutes break. Okay. Okay.
Any more questions? Anybody wants to ask something else?
I have one question.
Please.
Is
Yes.
the free product of Turner group is a Turner group again?
The free product of Turner groups. I think so. That should be true. Okay, you see, the thing is that I have done these things many years ago. So during the last 2 years, more or less, I haven't thought for this stuff. But yeah, I think that, so as Professor Said said, so there are some works for free nilpotent from free solvable groups, but there are some PhD theses of Turner students who have studied, let's say, like free products. And I think that in the case of free products, it should be a Turner group, right? But the thing is that, okay, since I'm giving a talk in Brasilia, I think that one should know, actually, it's an interesting thing to see what's going on with these groups acting on spherically rooted trees. Which of these groups are Turner groups and so on? Because you see, if you have a Turner group, and there we have residually finite P group. And one nice observation is that if you have a pro-P just infinite group, right? If you have a pro-P just infinite group, a pro-finite just infinite group, then every infinite order element is a test element. So if you have those groups acting on residually free groups, if you have their groups which are Turner groups, and in the pro-P completion, then you know that every element of infinite order, in the case of just infinite case, it's a test element, then you can obtain test elements back. But to be honest, I have never thought more serious. Maybe I thought 2 or 3 days and that's it. So at some point we stopped thinking about these things. We've got many results. We haven't published many things, but we really stopped to think in this direction. We wanted to do something else at some point. But there are many interesting questions in that direction.
Any other question?
I have a question.
Please, Cedric.
Sorry.
There's a connection with the Jacobi conjecture, no? The Jacobian.
Jacobi.
How do you test if an endomorphism is an automorphism?
Yeah, actually.
And the question of the Jacobian.
Yeah. I think that's true. Exactly. This is a question of Jacobi. Yeah. So I think that what Professor Said actually wants to say is that actually when you want to test that an endomorphism is an automorphism, it's a question of Jacobian. And this is true. Actually, Spielrein, when he, in the original paper, when the concept of a test element was introduced, exactly Spielrein uses, relates it to the Jacobian, right? So one uses like Fox calculus type of things, obtains a Jacobian and really sees, you know, when it is invertible, what's going on and this kind of thing. This is true. And of course, actually, when people in Lie algebras or polynomial algebras, recently they are doing a lot of work in this direction, they also use Jacobians in order to deal with these kind of questions. That is true. Yep.
Enrique, you wanted to ask the question.
Yes.
Yes. I just wanted to ask, Professor, if you think the retract avoidance theorem also has a pro-p analog.
The retract avoidance theorem has a pro-p analog. How do you mean pro-p analog?
I mean, if, for instance, if it holds for free pro-p groups.
No, for free pro-p groups, it's automatic. Because
It
you
is?
see, yes, because in free pro-p groups, every retract is a free factor.
Yes.
So here it's an interesting exercise. So if you have in a group, right, if a subgroup is contained basically in a union of free factors, then it must be contained in one of the, so in the free pro-p groups, it is true and you can prove it. But in other places, you know, okay, one can still ask such a thing. But you see, the whole thing, so this Bergman's question, if Bergman question would have a positive answer, many things that we obtained in pro-p groups, we could obtain in the case of free groups. Because this is exactly, when you have a free factor, you intersect it with a subgroup, you obtain a free factor. And one holds, the same thing holds with retracts, but with retracts it does not hold. So that's why it's completely different, and the theory is not so famous in the case of free pro-p groups. But it's a nice question that you asked. That's true, and it is true that it holds. Think about it, and I think that you will realize it by yourself, the proof.
Okay, thank you.
Any other questions? Yeah.
Probably, I remember that Mikhailov and Spielrein studied retracts and these for free Lie algebras also. Maybe it makes sense to extend something in the Lie algebra world, some ideas.
You see, the thing is that I think that, yes, people had mentioned there is one also Asian guy, I forgot, you maybe the name. They wrote a book in 1999, I think, where, okay, they gave all these ideas, actually, test elements in group theory, then test elements in polynomial algebras, and they related also with algebraic geometry in these kind of categories, right? But I think that in Lie algebras and in polynomial algebras, people are doing a lot of work, right? So they are writing a lot of many papers. But what was our idea here? So when I say why we stopped thinking here is that, okay, one may ask many questions, but here it turned out that the idea of test elements in pro-p groups, in free pro-p groups, gave a very nice thing theory, which you cannot get in other categories, right? And it was difficult. So those geometric questions which I discussed today, it was very difficult before to attack. So that's why they were not solved. But with this approach, it's working nice. But the thing is that many things one cannot generalize. And I can say that in general, in the Lie algebra context, things are slightly easier because things are linear, right? So this kind of thing, but in non-commutative things, let's say like here, in the case of retract avoidance theorem, it was a really surprising result. You see, you will never expect that such a thing will hold, but it holds. But anyway, I am not familiar about things that has been done in, okay, I know like a couple of things, but I never really studied, but I know that there are, I can say maybe 100 papers written for Lie algebras and polynomial Lie algebras, which involve test elements and this kind of things. But the original idea of test element was, as Professor Said mentioned. So the idea why one should study a test element, the idea is the following. If you have one related group, right? And you have some kind of automorphisms there. And basically you want to lift these kind of things to the free group in some sense. And then you see what's going on with these elements here, how it acts. So basically this was the idea. And if you look at Nielsen, why Nielsen was interested. So in free groups, this is really a very natural question. In free groups, it's an amazing natural question. And the fact that commutator x1, x2, why Nielsen needed this result? He thought about this in order to show that to study the IA, automorphisms of free groups, right? So that's why I started from there. But of course, one is allowed also always to make analogy in other categories and to try to see what's going on. We never know what kind of surprising things may occur.
Well, if not, then let's thank speaker again.